a very important group of paleontologists in Flinders University. We've created one recently in Adelaide, and I think there's a general interest. We just had a fossil festival at the South Australian Museum, and there were hundreds or thousands of kids asking how to become a paleontologist. So there's one here. Thank you for coming. Well done. So there's many people out there interested in paleontology in general, and fossils and evolution. And the other thing that it helps is to see where each of us is working, what groups are here in South Australia that are working, and maybe we might hear from groups in other places around Australia. In any case, I put up my hand to present a very brief review of where we're at in Ediacaran and Cambrian studies in South Australia. Let's start by indicating where most of those fossil localities, the ones that we're basically working on, are. The Ediacaran Flinders ranges, the Ediacaran rocks, which are in a package that in a package that includes from the Cryogenian all the way into the Cambrian. So it's not just the Ediacaran, but it's the Ediacaran that's most famous for up in the Flinders ranges. And we're also working in the Cambrian Lagerstätten in northern Kangaroo Island that's producing some amazing fossils. It was discovered early in the 1950s, but we revitalized that project in 2007, and we've been digging there since. So in order to put that into a time perspective, the Ediacara biota from the Flinders Ranges dates at about 555 million years. Then we've got the Emu Bay Shale at about 513 in the Cambrian. And then we've got a couple of other localities that will give you some reference points for those that study younger rocks. In South Australia, we're really well known for our Cretaceous opals with the ichthyosaurs and plesiosaurs, and obviously the megafauna that many of you work on. What does the Ediacara biota, how widespread is it, and how many taxa are known? Well, as you can see here, it's really widespread. It's known in at least 30 localities in the 5 continents, and hopefully there will be some in Antarctica. That's something that I'm trying to develop for the future. There are about 35 genera plus, and more than 100 species, but a lot of those were probably, it's a bit of oversplitting. But you can see here, this is the Cryogenian, the last glaciation of the Cryogenian, and we get into the Ediacaran. And towards the end of the Ediacaran, we start getting the presence of some taxa. If you look at that, these are various sites in Newfoundland, etc. But you can see that Ediacara is the one that presents actually the most diversity. It's got from radiomorphs and ernietomorphs, Chinodiscus, and then the bilateral, discoidal, triradial, tetraradial taxa, etc. And towards the end of the Ediacaran, all of these taxa disappear. Totally. There's a couple of instances, 2 or 3 instances of things that do resemble Ediacaran forms, but whether they are proper Ediacaran fossils, that's a different story within the Cambrian. What do these animals, organisms look like? Well, the most emblematic, the better known ones are these ones here, Tribrachidium, 3 branches. It's about, the largest one's about a 50 cent piece. Sprigina, Parvancarina with the shape of an anchor, and Dickinsomia. And if you were as lucky as to find one slab preserving these and some of the others, this is what it would look like. That's basically the type of rock that we find it. It's sandstone with a patina of red from the rust up in the Flinders Ranges through hundreds of years exposed. But those are mostly negative impressions, as you can see here. But obviously the organisms would have lived in a very different environment. We believe this would have been very shallow, warm waters around the equator at the time. We have evidence of wave action and ripples in some of the beds, etc. So we're looking at shallow waters compared to the older Ediacarans from Newfoundland, which are much less diverse than ours and are at about 1,500 meters of depth. So what we're seeing here is that we're seeing organisms that have a connection to that microbial mat that is the one that ultimately allowed them to be preserved. That those microbes were the ones that had a basic relation with the organisms by coating them and allowing those soft bodies, they're all soft bodied, to be preserved in sandstone, something that hasn't happened since the Ediacaran. A few years back, we put a proposal to choose the state fossil emblem from amongst the Ediacaran forms, and in particular these well-known ones. As some some of you might know. Do you know which one got chosen?
Springina.
Very good. Indeed, Springina became the state fossil emblem for South Australia 3 years ago. And this is part of what we're trying to develop in our state regarding these early communities. So one interesting idea is that when these fossils were first found, they thought that they belonged to animals, that they belonged to very simple forms of jellyfish, very simple forms of annelids, very simple forms of arthropods. However, in the 1990s, Sarker proposed that there could be a different alternative interpretation for at least some of these organisms. And as we know, the three multicellular organisms known today are plants, fungi, and animals. But he proposed that there could have been a fourth one that got wiped out when competition from animals became intense during the Kingdom explosion and therefore disappeared. He called it the Kingdom Bendabionta. And this is what he proposed. In the center here, you can see a structure of an air mattress. That's how he visualized that these organisms could have sustained their body shapes and not collapsed under the weight of the sand that buried them alive. And that they could grow in various arrangements. They could have bipolar growth, like fractofusus or Dickinsonia. They could have radial growth, like Tribrachidium, Saccharomedusa, or unipolar, as you can see here, like Springina. Do we have a pointer?
No, not
This is
yet.
the only one, because I think I'm running out of battery. Anyway, so these are various interpretations. Some of these organisms, we have evidence, alternative evidence, that they might belong within the animal group. But this is a very interesting, typical Sarker idea. He was thinking outside the box all the time, and he came up with very interesting propositions, and this is one of them. Part of what he was proposing for the Bendabionta, and why he was thinking that they were not either of the three, is because they have a really different mode of growth that is not conducive or not present in animals, and that is fractal growth. And this is present in all the arrangements. And our colleagues from Cambridge, Jenny and Sam Congamoris, they tried to see, okay, if we're going to generate a shape, how many steps do we need to actually produce something that has some resemblance to those ediacaran forms? And actually, from the first step, branching to the right, to the left, branching twice, branching 3 times, etc., changing those parameters, they were capable of producing forms that are not unlike those found in the ediacaran. So much so that in one of their papers, they actually see very good repetition of some of the forms that we find in the ediacaran. So this might be indeed a fourth kingdom present in the ediacaran, together with some animals as well. There is evidence of animals in the ediacaran, but those animals are all soft-bodied, except right towards the end of the ediacaran, and they basically are very, very small, leaving trace fossils and exploiting the organic material in the sediment. Whoops. So this is a, let's see if that's going to show. There you go. So this is the Alpina fossil site, and these are the fossil, the tennis courts that we call them. These are basically seafloor beds that have been turned over, and as you I haven't explained, but the way these organisms are preserved, they're living on the seafloor, covered by sand, and the sand is in the underside, the fossils are in the underside of the beds, so we have to turn them over. And this is just, this is what we call One Tree Hill. You can see the beds along there, and we're looking at various assemblages through time. Those down there were tennis courts and tennis court north, and this up here is what we call One Tree site, with a different group of organisms. All those beds are covered with fossils. One of our students, Felicity Coots, whom some of you probably know, studied large slabs from Ediacaran Conservation Park, not from the Alpina, which is the one I've just shown you, and actually saw that some of these individuals, in particular Parvancorina, which is very, very common in this large slab. This is the Australia slab that is up in the Ediacaran Gallery of the South Australian Museum. She looked at it in very fine detail. She latexed it, and with low under light, she was able to pick up all the individuals, all the fossils that could be recognizable, and actually studied the orientation of Parvancorina with the current, taking the current to be the following from. and she realized that there was a significant orientation to that. Another one of our students, Lily Reed, she's looking at a broader picture, assemblages and presence and absence of various taxa and their turnover across the Ediacaran localities of the Flinders Ranges. And she's realized that there is a fascies-specific assemblage. So some organisms are appearing in some of those fascies, but not in others. And she's studying that, and she's able to produce or recognize particular groups of taxa that are present in one and not the other. So the South Australian government has realized that this is a very, very important site. It's been taking a long time to come to this, but in the last South Australian government, they put up an action plan to preserve and develop all that has to do with South Australian Ediacaran fossils in the Flinders Ranges, and among that, the possibility, and that's what we're working on now, to nominate the Flinders Ranges as a UNESCO World Heritage Site. Naracoorte is already our only UNESCO World Heritage Site for fossils in South Australia, and we think there is a good case for proposing the Flinders Ranges all the way from the Cryogenian through the beginning of the Ediacaran with the GSSP, all of the Ediacaran, the presence of the Ediacaran biota, and on to the Cambrian, the onset of the marine oceans similar to what we understand today. Something that happened in developing this idea just happened exactly a month ago was that the South Australian state government has purchased Nilpena Station, the western side of Nilpena Station, to fuse with Ediacaran Conservation Park to further protect the fossils of those that I've shown you in the video. They are, to this day, they were in privately leased station, cattle station, and this is the way to protect them further. Let's move on to the Cambrian. So what does the Cambrian explosion mean? You've probably all heard of it. And what it means is that we have what it represents, a rapid densification of animals. In the Ediacaran, there are animals. They're not very common. They tend to be very small. Some of them are going towards, and we can discuss the presence or absence of cholesteroids in Garcia, a paper that came out in Science last year. But they're not the animals we know today. How do we know? Okay. So anyway, the Cambrian explosion brought a whole range of new aspects, not the least predation and the skeletal animals. Quickly, we'll go over what happens. If only you have to take one home message from this, is that the phyla and the classes were basically, in our planet today, basically appeared during the Cambrian. That's the Cambrian there, that's the present here, and there's the blue is the phyla, and the yellow is the classes. Not so much at other levels. The Cambrian explosion is mostly at the higher taxonomic levels. Regarding sub-body preservation, this is what we normally find in the Cambrian locality, all with mineralized exoskeletons. And what we want to look for is this other thing. These are both representing the Bellido shale, but we've got a similar place in Australia. The oldest such locality with sub-body fossils is Shenyang in China, and then we've got Emu Bay in Time, Emu Bay here in Australia, the Bellido shale in Laurentia, and then a number of other smaller sub-body fossil localities. So this is our fossil locality in Kangaroo Island, northern Kangaroo Island. This is called Back Quarry in particular. It's within the Emu Bay shale, and it's produced a whole range of fossils. The most common fossil is the trilobites. I'm not going to discuss much about them, only tell you about this smaller one that Jimmy is working on now. This is Stanzbylobata, very, very common. How common? Well, it actually reaches densities of up to 300 individuals per square meter in some beds. We have a number of very important discoveries from the Emu Bay shale. Not the least this one. This was the first, one of the first complete examples of a fossilized eye, and actually there's 500 million years between those two organisms, but they're not related. That is obviously an insect, and this is a marine organism, probably related to, well, it's really large, and we're still discussing what it might belong to, because we find it isolated. And then we found also the eyes of this a big animal, and why do we know it's about, the eyes are about that big, and the only animal that could have eyes that big in the Cambrian is Anomalocaris, and we counted the lenses. It's got about 30,000 lenses in its surface, and that got published in Nature and got the cover. And to finish up, some late discoveries. One of them was this strange group of organisms called the tunicolians. And what we realized when we did an analysis is that they actually fall close to us instead of an arthropod. That tail, which was the laser pointer, that tail was originally thought to be an arthropodian structure, but no, it's actually closer to tunicates. As you can see here, it's not much different from a tadpole larva. And something that Jim and Jimmy led research piece that Jimmy led was looking at other evidence, not only in taxonomy but also behavioral. And we were looking at the molting on trilobites, both Stangia and Religia. And this is a graph from it, looking at how, because this is one of the only places where you can do it, because there's been very little disturbance of those fossils, what sort of arrangements, what sort of modes of exuviation were present in these early trilobites. Anyway, the last but not least, we've done a drill core through it with money from funding from National Geographic, and we got to the fossil beds, as you can see there, at about 95 meters of depth. We intersected the fossil beds. There's 3 Religia trilobites in there, and that's one of the next steps is looking at the geochemistry. This is a very clean, unweathered sample, and we're going to be able to get proxies to understand levels of oxygen, levels of organic matter, iron, sulfur, etc. in the water column of the Cambrian. And I need to say that this is obviously teamwork. You can see a number of our team members here, plus Marianne Binney, who's present in the room, and Jimmy. And this is a collaborative effort between many groups. We've got colleagues from other universities that have come here, and obviously we need funding. We've used funding from various sources.